Welcome to our presentation on ARFIMA models. Today, we will explore how to analyze and model time series data that exhibit long memory, a common characteristic in economics and finance. Long memory processes are stationary processes where the influence of past shocks decays much more slowly than in traditional short memory models. This has significant implications for forecasting and policy analysis. For instance, think about inflation. A sudden oil price shock might not just affect inflation for a few months, but its effects could linger for several years, slowly diminishing over time. This is a classic example of a long memory process. To understand why this is important, let's first discuss the memory problem that often arises in economic data. When analyzing economic data like GDP, stock volatility, or inflation, we often face a dilemma. Standard ARMA, autoregressive moving average, models assume shocks fade away exponentially fast, which we call short memory. This is often unrealistic. On the other extreme, ARIMA, autoregressive integrated moving average models, with a unit root, assume shocks persist forever, which is infinite memory. This can also be too extreme. The reality for many economic series lies in between. They exhibit long memory, where shocks are persistent and linger for a long time, but do eventually fade. ARFI models are designed to capture this specific behavior. Standard ARMA-ARIMA models force you to choose between either short or infinite memory, which can lead to misidentification of the true decay pattern. As you can see in the graph, the exponential decay of ARMA is very quick, while the infinite memory of a random walk never decays. The hyperbolic decay of an ARFI model, shown in blue, accurately represents the slow, persistent fading of shocks observed in many economic time series. Misidentifying memory leads to incorrect impulse response analysis and poor long-term forecasting. This flowchart provides a clear path for model selection, building on our discussion of the memory problem. We begin our analysis with the time series data, YT. The first crucial step is to test for stationarity, commonly using tests like the Augmented Dickey-Fuller, ADF, or Phillips-Perrin, PP tests. This initial assessment guides us to one of three main categories. If our series is found to be stationary, or I0, and its autocorrelation function decays quickly, a standard ARMA model is suitable. Here, the integration parameter D is 0, corresponding to an exponential decay pattern for shocks. On the other extreme, if the series is strongly non-stationary, or I1, we typically apply first differencing and use an ARIMA model. This implies an integration parameter D of 1, leading to infinite persistence of shocks. The crucial middle ground is for series that are stationary but exhibit a slow, hyperbolic decay in their autocorrelation. This is the domain of ARFIMA models, where the fractional integration parameter D lies between 0 and 0.5. As the takeaway highlights, ARFIMA models offer a solution for avoiding the tendency to over-differentiate stationary series that exhibit long-run dependence. It's therefore vital to check for fractional integration before defaulting to first differencing to accurately capture the series's memory characteristics. The core of the ARFIMA model is the fractional differencing operator, represented by 1 minus L to the negative D. Here, L is the lag operator, and D is the fractional integration parameter. This equation demonstrates that an ARFIMA process is essentially a standard ARMA process applied to a fractionally differenced series. The crucial aspect is that D is not restricted to be an integer. It can be any real number, providing a flexible spectrum of memory persistence. This parameter D captures the long-run dependence, or the long memory signal, while the AR and MA terms handle the short-run dynamics, or noise. The value of D is key for interpretation. If D is less than 0, it indicates anti-persistent or intermediate memory. When D equals 0, we have a short memory standard ARMA process. The most interesting case for long memory is when D is between 0 and 0.5, signifying a stationary process where shocks decay slowly. If D is greater than or equal to 0.5, the process becomes non-stationary with infinite variance. The autocorrelation function, or ACF plot, is our primary indicator for detecting long memory.
If the autocorrelation bars remain significant far out along the lags, showing a slow, hyperbolic decay pattern, it's a strong signal to suspect an ARFIMA model is appropriate.